Welcome everybody to GeoHug. So before we kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am thrilled that we have Catriona Breasley joining us today. So Catriona is a final year PhD candidate at the University of British Columbia and principal consultant at Catriona, specializing in pegmatite mineralogy and geochemistry. And with her expertise, it is going to be brilliant learning from her about lithium pegmatite mineralogy and geochemistry, a key to efficient exploration, mining, and metallurgy. So this is going to be a fantastic session. I hope you do all enjoy it. I will be promoting you up as panelists throughout the session. If you're able to jump off mute for the discussions at the end, please don't be shy. Say yes and come on through. But yes, thank you so much, Kat, for joining. It's really awesome having you here today.
Yeah, thank you so much for having me. Yeah, I think it's going to be a great session.
Yes, I'm very excited that you've joined us, so thank you for that. But I was really curious before we started what got you into geology to begin with.
Absolutely. So I think with a lot of us that uh, who are interested in geology, it stems from their childhood. So I grew up on a tiny island on the west coast of Scotland, which was actually a historic slate mine. And I remember searching on the beaches and finding these gorgeous cubes of pyrite just washing out of the stones. It was really what sparked my interest, and that just continued through my life.
Oh my gosh, I love that. It's oh, that would have been really special. I've always wanted to go to Scotland, so I'll definitely have to hit you up and get all the good spots to go so I can see it for myself. And so you have traveled around a bit now, living in Vancouver. What's been some big career highlights for you so far?
Yeah, so I think one of my favorite career highlights happened this past summer where I got to lead some field trips to the Pegmatite in Manitoba, and it was linked with the GACMAC conference. So I got to take a bunch of very excitable pegmatite enthusiasts underground at the mine and show them around. And it was just really special seeing their amazing reactions to the rocks and just chatting with other experts in the field. So many great ideas were shared. So I'd say that's definitely one of my peak career highlights so far.
Oh, I love that. That is awesome. Have you got many more adventures like that in the pipeline?
Ooh, currently I'm trying to focus on finishing up my PhD, but when I'm done,
It's
I'm
quite a
really
task.
excited.
Yeah.
It is. I'm really excited to dive into the world of exploration consulting and geoeducation further.
I love that. And I'm very curious what favorite pet rock you've brought along for us today.
Oh my gosh, I brought a few pet rocks, but I'll be very quick with
I
them.
love I
They're
love when there's many. Bring it on. Yeah.
Absolutely. Well, a lot of people who work in lithium pegmatites know that there are a lot of minerals that are all white and look very, very similar. So I brought a suite of my 50 Shades of White sequins to show you. So the first one being a gorgeous spodumene mass from
Wow.
Tanko. This is the main lithium ore that they mine there. And some another big white rock. This one's amblygonite, which is a lithium phosphate. A slightly smaller white rock, which is the case bar. And I have a few more on my desk, but maybe I'll just end up on this one, which is pollucite, which is the main cesium ore you're looking for when you're mining pegmatites.
Wow. As a non-geo, they all looked incredibly like similar to me. So I'm like, the fact that you can all tell the difference between all of them is pretty awesome.
Yeah, it does take a trained eye to really get
I
your
bet.
eye and pick these different ones apart.
Oh my gosh, that's so cool. I love that. Well, yes, thank you so much for joining us today. It's awesome having you here. And yeah, if you want to share your screen and we'll get stuck into it.
Thank you so much, everyone, for coming along today. I'm really excited to share some of my experience in pegmatite mineralogy and geochemistry, and specifically how you can use this information to streamline your exploration efforts, train your teams, and ultimately help guide your mining and metallurgy at the end of the day of your project development. So to give a bit of a brief overview, today I'm going to be talking about, firstly, the importance of mining pegmatites. I'm going to mainly be focusing on lithium in this talk, but there are various commodities you can also mine from pegmatites. and their demand is expected to increase in the future. Then to really start us off, I'll give a bit of a brief background about what pegmatites are, their typical mineralogy, some of the key processes that occur in pegmatite crystallization and metasomatism, and finally, some geochemical diagrams and how you can use these to help pick apart your paragenetic sequence of your pegmatite. Then I'll be really diving into the mineralogy section, and I'm planning on talking about 4 major mineral groups today: the anhydrous lithium aluminosilicates. So when I say this, I mean your spodumene, pethite, your cryptite. I'll then be talking about your tourmalines. Finally, I'll talk about some micas and niobium and tantalum oxides, and then some other interesting minerals as well. I'll end up the talk by talking about 3 main aspects of the industry. So how this information can be used in exploration and in mining and in your metallurgy for when you're processing your minerals. So the star of the show today, as I said, is really going to be lithium. And lithium is a fantastic element because it's very light, has a high energy density and a high electrochemical potential, which makes it fantastic for use in batteries. So specifically rechargeable batteries in cars and in other uses. Lithium has other uses as well. It can be used as an additive in ceramics. And for this, you're looking for a really pure lithium concentrate that has a low iron content, which is important to remember for later. And you can also use lithium in various medications. Despite fluctuating markets over the past few years, it's clear to see from this new graph that was put out by the International Energy Association in 2024 that the demand for lithium is going to increase a lot over time versus our supply. And at this point, it's also really important to point out that there are other commodities you can mine pegmatites for, such as tantalum and niobium, cesium, high purity quartz, feldspar, and tin in the form of cassiterite, just to name a few. So I've taken this IEA graph here and blown it up. And just so everyone knows, NZE stands for net zero emissions and APS is the announced pledges scenario. And I've highlighted the difference between the demand and the supply in red to just show this huge difference that's going to happen over time. And to account for this, we really need to have efficient exploration, mining, and metallurgy of our pegmatite deposits. To do this, we need highly trained teams with experts in what I call the 2 pillars of pegmatite: exploration and processing, your mineralogy, and your structural emplacement. Today, I'm mainly going to be focusing on the mineralogy. And for this, overall, we need to have a good understanding of pegmatite systems. So going right back to the beginning, what is a pegmatite? A pegmatite is an igneous intrusive body which can contain highly variable crystal sizes, from microscale, where you can't even see the minerals in hand sample, all the way up to macro scale. So the picture I've shown on the right here is me standing in front of some ginormous spodumene crystals from the Plumbago deposit in Maine in the United States, which I was really excited to see. And it's important to note the crystals can get bigger than this as well. Pegmatites often contain interesting textures which are relevant to their unique formation conditions. And 2 examples I'm going to talk about is comb structures. So comb structures are oriented minerals that crystallize along the surface of a contact in a pegmatite. So this can be along a country rock to pegmatite contact, forming these nice oriented crystals. However, it can also be between pegmatite zones, and also I found them around individual crystals in a deposit as well. Another interesting texture is graphic intergrowths, which are these complex intergrowths of feldspar and quartz usually. However, you can also find them with tourmaline in quartz and mica in quartz as well, just to name a few. Pegmatites are really interesting and cool because they can contain significant incompatible element mineralizations such as lithium, cesium, and tantalum, or the LCT pegmatites, which I'm focusing on today. And I think the pegmatite community can generally agree that there are 2 main methods of pegmatite genesis: fractional crystallization, which is your igneous parent body crystallizing, and then your pegmatite forming as the incompatible elements concentrate in your residual melt. Then your pegmatites are emplaced. The second method is anatexis, which is the partial melting of country rock. And recently, I was part of a team that put out some really exciting results that show that to get lithium concentrations to a high enough level to crystallize economic pegmatites or spodumene-bearing pegmatites, you really need this multi-stage distillation process where you have a pre-enriched source that's already enriched in lithium melting again to form your pegmatites. And my colleague Lot Koopmans wrote that paper, and I highly encourage everyone to go check it out. So in general, pegmatites are fairly common occurrences across the globe. However, most are made up of just quartz, feldspar, mica, and garnet. And you can see on the right here, here's a hand sample showing your nice black schorls and your feldspar matrix that's hosting it. Within that group, there's only about 0.1%, which are rare metal bearing. And within that further, even less are lithium mineralized. When you are thinking about the textures of pegmatites, they can broadly be grouped into three main groups. So you can have simple pegmatites, which contain a uniform texture and mineralogy throughout. You can have zone pegmatites, which have discrete zones, which can be mineralogical or texturally variable. And these commonly include a border zone, a wall zone, and some various intermediate zones. And finally, you can have complex zoned pegmatites, which are essentially your zoned pegmatites. However, they incorporate significant contents of metasomatic overprint. And I've shown on this diagram on the screen here two various types, which are really commonly seen in pegmatites. Your metasomatic units, which follow the boundary between two zones. Albertization commonly does this. And in the upper right-hand side of the figure, you have this patchy, pervasive replacement unit. And complex pegmatites are really what I'm going to be focusing on today, with a lot of examples from the Tanko pegmatite in Manitoba, which is where I researched for my PhD. And I'm going to be talking about the complex pegmatites because at the end of the day, they are the most complex, as is their name. And therefore, it's kind of difficult to understand them unless you know some of these principles that I'm going to be talking about. So usually two major processes occur in pegmatite paragenesis. So typically we see this first stage of primary magmatic crystallization where you get these blocky crystals, you can get apatite, which are then followed by various metasomatic events. So I've put three really common metasomatic events in lithium-bearing pegmatites on the screen here. You can have albertization, which is a sodium-enriched event, which acts to usually replace blocky primary K feldspars. Then typically later in the metasomatic sequence, you can get more lithium-enriched metasomatic events, and these can precipitate lepidolite. And also you can get MQM alteration or muscovite and quartz replacing microclines. And metasomatism is really important in pegmatites and being able to distinguish these features because they can act to concentrate or deplete elements, which is going to affect the economic viability of your deposits at the end of the day. So I've put two rock samples on the screen here, the upper of which shows the apatite albite zone from Tanko, which is quite debated, but I personally think it's a secondary overprint, and this shows enrichments of tantalum, and that's one of the main zones that Tanko targets for mining of tantalum. And also on the bottom here, muscovite and quartz also has elevated tantalum at the Tanko pegmatite as well. So geochemical evolution is very important for understanding pegmatite systems because essentially the more geochemically evolved your melt is, the more likely you are to retain your incompatible elements. So when you have an igneous intrusive body crystallizing, typically the elements that you're going to crystallize out first really like fitting into crystal structures. So this can be iron, potassium, magnesium, to name a few. And then essentially your system concentrates your incompatible elements that have either a weird size or a weird charge balance in the elements themselves. You can take the geochemical points of your mineral data and plot them against some established diagrams in pegmatite literature, such as the potassium and rubidium ratio versus your incompatible or compatible element. This should show your nice linear trends, which can help inform on your paragenetic sequence. You can simply plot elements against one another to show similar trends. And there are some established diagrams in literature, which I'll go on to talk about a little bit later. And again, the more evolved, the better, because the more likely you are to have enough lithium content in your melt in these really geochemically evolved systems to crystallize pegmatites that you want to target for mining. Here is another overview of the various minerals I'm going to be talking about. And I'm just going to dive straight in with the lithium aluminosilicates. So these are the minerals usually mines really hone in for mining because they have a lot of lithium within their structure. Spodumene, pestilite, and eucryptite all exist in pressure and temperature space within one another. So spodumene can be seen as this higher pressure version in the system. Pestilite is typically the lower pressure version, and eucryptite forms this small field to the lower left-hand side of the diagram. And because of these relationships, they can be used as a pressure and temperature indicator in pegmatite systems. And as I've said, these are great because they're the main source of hard rock lithium and pegmatite as well. So I've put in two examples of some lithium aluminosilicate mines that I've been to before. So the first I'll talk about is the petalite mine at the Li-Pegmatite in Namibia, which I was lucky enough to visit on a field trip recently with SEG. So the Li-Pegmatite is primarily mined for its cassiterite content. However, it does have a lot of petalite in its system as well. And because of this, it's assumed to be a lower pressure system. And petalite is a really interesting mineral because it can't take iron into its structure at all. So this means it's great for ceramic lithium concentrate uses, because when you process the petalite, it's going to be a very, very pure concentrate at the end of the day with a very low iron content. And they also have a lot of tantalum mineralization. So that was a really interesting mine to visit. And the Tanko-Pegmatite mines spodumene. And I've shown the outline of the pegmatite on this diagram on the right-hand side at the top, just the outline of the pegmatite, because it does not outcrop at all. And it was a completely blind discovery, which was noted by a tin anomaly in the region at the time. And I've put a cross-section through it and shown that on the screen as well, where I've colorized the two main lithium-bearing units, the lower intermediate zone and the upper intermediate zone, which is zone 50, which is just almost bulk spodumene mineralization. So the spodumene at Tanko can be found in multiple textural forms. You can have primary spodumene. However, the bulk of mineralization is found as spodumene and quartz intergrowths. And in general, the system is very iron poor. So there's a low iron content of the spodumene in almost all cases. And Tanko has been mined throughout the years for various commodities. For tantalum, for cesium, it's the largest pollucite deposit in the world. However, nowadays they're really targeting the lithium mineralization in the spodumene. So I mentioned that a lot of the spodumene is within SQUI, and here is the proposed breakdown path that formed the Tanko deposit mineralogy that we see today. People think that there is this mass crystallization event within the petalite stability field. And as the deposit cooled over time, this crossed into the spodumene stability field, and there was this mass re-equilibration event forming these spodumene and quartz intergrowths, which was then followed by a generation of primary spodumene crystallizing and then a very minor amount of eucryptite. So in an ideal closed system breakdown, we would expect to see petalite breaking down into about 56.4% spodumene and 44% quartz. However, is this what we see? It's kind of tricky to answer because it's such a big deposit, but essentially it's sometimes, but not always. And this is what some of my research focuses on. I found lots of evidence that the SQUI might not actually be linked to parental petalite breakdown based on the presence of green spodumene in spodumene and quartz intergrowths, which is indicative of elevated iron contents. There are virtually no reduction in volume textures. This breakdown is associated with about an 18% volume change. There's virtually no pestite left in the deposit itself, and this breakdown path is based on some controversial fluid inclusion analyses. So the squeeze story is very much yet to be answered, and I think people should keep an eye out for a paper that I'm producing hopefully very soon that might answer or provide some more insights on this. So the squee itself is very texturally variable, which I've mentioned before, and I really wanted to put a slide about micro squee, which is a type of spodumene and quartz intergrowth that is really not good for metallurgy and mineral processing because it's very, very hard, and this leads to multiple issues in the processing cycle. So some of the workflow I did some thin section petrography, and it revealed that this micro squee was a micro symplectite, which cut into this primary generation of squee. So I then took the thin sections and put them under cold cathodoluminescence, which is a fantastic technique because spodumene really pops and shows the zonation. And it's really highlighted here that the classic squee shown in yellow on the upper left, which are these oriented intergrowths, is being cross-cut by the secondary generation of microsquee. And based on some geochemical analyses and some comparisons to other spodumene in the deposit, I probably think that this is how it's formed. You get your primary generation of squee crystallizing, and then you get this reactive fluid coming through later, which performs a coupled dissolution reprecipitation reaction, which is enriched in cesium and depleted in manganese and tin. So now I'm going to be talking about tourmaline, which is probably my second favorite pegmatite mineral ever. I've put some nice pictures on the screen here. I think tourmaline is great because it's a really nice and easy mineral to identify in the field because it's long, it's often very colorful in your LCT deposits. So I've got some schorls on the screen here, which are the black tourmalines, and some pink elbites. And also tourmaline, the gorgeous pegmatite trash can. So tourmaline gets a lot of flack because it can take almost anything into its structure. People think it's just a rubbish bin at the end of the day. However, that is really fantastic for recording geochemical information because it can take almost any element to its very varied crystal substitution sites. This means it can record the geochemical changes from the first stages of crystallization all the way up to metasomatism, given that there's sufficient boron in the system to crystallize the whole way through. So here's why I call it a bit of a rubbish bin. Here's the crystal structure and formula. There are lots of different substitution sites of various crystal sizes, element sizes. In LCT systems, I'm going to be talking about the alkali tourmalines, so the sodium excite-bearing tourmalines in this presentation, which is usually what you see in LCT systems. And the Y site is really the most important because that's where you can get this crazy different substitution in the system. You can get aluminium, iron, magnesium, lithium, manganese, titanium, just to name a few. So in LCT pegmatites, the typical crystallization sequence starts with your javites crystallizing first. So this is your magnesium-bearing tourmalines. This is followed by your iron-enriched tourmalines, your schorls. These are both usually black or brown or green in hand sample. And then this is followed by your elbates crystallizing, which have elevated lithium contents. I'm going to wave my red flag right now and say you can't really use color in tourmalines as an indication of their composition. However, usually when you see pink tourmalines in the field, it's a great sign that you have lithium mineralization. And when I say elbates, a lot of people think of these gorgeous pink tourmalines. However, when I put this diagram on the screen, a lot of people will look at this sample and think it's just a simple pegmatite, nothing special about it. It's just got some schorl, quartz, and feldspar in there. However, if you look at thin sections, there is microscale information in these tourmalines, which are actually elbate rims, which indicate that there's lithium mineralization in the pegmatite elsewhere, as well as in this just simple wall zone expression of the mineralogy. So another fantastic thing about tourmalines is that they can be heavily zoned, and multiple different types of tourmaline can coat one another when they crystallize. So given the boron content of the melt, they can crystallize from your border zone into your intermediate zone, into your final stages of magmatic crystallization, and they can also precipitate during metasomatic events. This is a individual crystal from this exact sample that I showed on the previous screen, which shows the Elbite's cores. So you can see the magnesium diagram, which is this multicolored map here from the EPMA maps. It shows a highly enriched magnesium core, which is then coated by an iron enriched rim in the map above. And then on the right, on the left, you can see the elevated aluminium and manganese contents, which are your Elbates. So this means that a wealth of mineralogical information can be recorded within a single crystal. And crystals exposed at the surface have these rims that are invisible to the human eye. So you really need to do your intricate geochemistry to find these trends, and they could indicate more lithium mineralization elsewhere in your pegmatites. You can take your geochemical information and plot it. Here's some examples from the Prof pegmatite, which is pegmatite I work on in Revelstoke in British Columbia, where I plotted the fluorine versus manganese and sodium contents. And essentially, they show this crystallization sequence exactly as we would assume, where you have your intermediate zone magmatic tourmalines crystallizing first, then followed by your central zone tourmalines crystallizing and your metasomatic ones crystallizing last, recording these changes over time, as shown by this overlay here. I'm now going to be talking about the micas, which are another very pretty mineral in LCT systems. They're sheet silicates, so they're nice and flaky and easy to identify in the field as well. So micas can typically be plotted on this ternary diagram in LCT systems, where you have muscovites in the dioctahedral form, which are elevated in aluminium. You can also have trilithionites and polylithionites forming, which are enriched in lithium. And these are the two technical mineralogical names of the lepidolite series. And I've put a picture of lepidolite up on the right-hand side of the screen here. In LCT pegmatites, sometimes you can get some iron contamination, usually from country rock, and you can get some zinnwaldite micas. And I've put it in inverted commas because it's been a disproven name. And again, you can take the mineralogy and take the geochemical points, plot them on these graphs. I've put potassium rubidium here, again from the Prof pegmatite, versus rubidium, lithium, and cesium. And again, we see these nice geochemical evolution over time where you have the border zone muscovites crystallizing first, then your intermediate zone micas, and then your final metasomatic micas. And again, an evolution trend overlain here. And typically you see early in lithium-bearing pegmatite systems, an early magmatic muscovite phase followed by later magmatic and metasomatic trilithionites and polylithionites, so your lepidolites. Now I'm going to be talking about the tantalum and niobium oxides, and I've put 5 pictures of some very common oxides on the screen here, purely for the reason of saying that they all look very, very similar and they're hard to distinguish in a hand sample, if not impossible. So they all look very similar, but they can reveal some really important information. And in some systems, this is what you're targeting when you're mining your pegmatites. They're an interesting mineral because they can precipitate both in primary and secondary forms, so in your magmatic or your metasomatic phases, and in both. So this is really important if you're targeting your niobium and tantalum in your deposit, because if you understand your paragenetic sequence, you can see where the bulk mineralization occurred of this element, and you can track it through time and see how much is deported and recrystallized in your metasomatic events. And this is important for metasomatism because fluorine is a common component that increases throughout the evolution of the system. And this can help complex tantalum and niobium to remobilize it. So this funky zoned mineral I put up here is a microlite, which is a tantalum oxide, niobium oxide as well, from the Tankopegmatite from the lepidolite zone. And again, they can show an evolution sequence, which I've overlain on this quadrilateral here. And this is one of the established geochemical diagrams I was talking about earlier, where you can have this transition over time and this geochemical trend of iron crystallizing out first and then manganese later in the system. And this can help reveal insights into when your bulk mineralization occurred. However, it's very common to see disjointed trends on this quadrilateral because crystallization of these oxides can be influenced by different minerals crystallizing elsewhere at the same time in the system. For example, garnet is known to buffer the manganese content of the system. And also they're great uranium-lead geochronometers. So there are other minerals, which I will not be talking about today, such as the phosphates. And I put this meme up on the slide here because there are thousands and thousands of secondary phosphates that I don't know anything about really because they're so complex and they're really difficult to analyze. I have huge respect for the pegmatite researchers that focus on phosphates. However, I will briefly mention one, which is the amblygonite montebrassite series, which is a lithium phosphate that can be mined for lithium. Quartz is also a really interesting mineral that often gets overlooked. There's some fascinating research coming out at the moment about the trace element content of quartz and how it can be used as an exploration proxy in the field. And I'll just touch on polysite as well. I've said before that it's the major cesium-bearing ore. And you can see it's being cross-cut by the secondary metasomatic mica. And this is from the polysite zone in the Tankopegmatite. So bringing this all together, figuring out your mineralogy is really key to understanding your deposit, especially in pegmatite systems, which are highly complex and not very well understood in the grand scheme of things. So understanding where your minerals are concentrated is very, very important for multiple reasons, for exploration reasons and for mining and metallurgy. Finding out the element that you're targeting and whether it's in its primary or secondary unit, so whether it's magmatic or metasomatic, helps you understand where the minerals are concentrated so you can target it better. Finding out these mineralogical relationships in the different zones within your pegmatite is also important because there can be some reoccurring relationships, such as the presence of two zones that are always beside each other and coexisting. And at the end of the day, this early stage information and finding out your paragenetic sequence is information that can be transferred into the field where often pegmatites are geochemically linked and similar trends can be seen. And also, back to this rock again from Revelstoke, pegmatites, which might usually be ignored on the surface, which could look barren, can reveal treasures at depth. So now I'm going to be talking about more of the industry side of things and how we can take this mineralogy and geochemistry and implement it into a real life setting where we're in the field and we're exploring for pegmatites, for example. So I just briefly mentioned about defining your paragenetic sequence. This is really important because it also lets you be able to identify your minerals in the field better. So it's all great if you go into a pegmatite field with your handheld instruments like your Raman or your handheld XRF and just zap all the minerals you see. However, it takes a trained eye to be able to pick out which minerals to zap in your deposit. And because all of them look so similar, especially in lithium systems, having a trained eye to pick out this specific mineral phase that you're looking for is very important. And the inside of a pegmatite influences the outside. So geochemically evolved systems and LCT pegmatites often have geochemical halos associated with them, where metasomatic fluids get pushed out into the country rock, which can be used for exploration purposes. Now, geochemical halos from pegmatites have been studied in the past by a few authors, such as Morgan and London in 1987. They did a great paper on the zonation in the mesosomatic overprint surrounded in the Tanco-Pegmatite in Manitoba. But a great summary was recently put out by Marcus Sweetapple in 2024, which shows an overview of these different systems. But I would love to zone in on two based on their various country rock settings. So first I'll be talking about exomorphic halos and metasedimentary sequences. So there is a pegmatite field in Spain and Portugal, which really shows great relationships between your mobile elements which go into the country rock. So you have your fluorine, boron, lithium, rubidium. You guys can all read the rest of the elements, but they have been pushed out into the country rock and they go various distances. And they found in this study that anomalous concentrations can be found about 4 to 5 times the intrusion size away from the deposit itself. So a 20-meter wide pegmatite can have a halo that's up to 100 meters wide. So that's really exciting for exploration purposes, because at the end of the day, we want large pegmatites that we can mine easily and economically. And another great thing is that larger halos are associated with the most fractionated pegmatites in the system. And this paper also put out some mineral exploration indicators. So I've put them on the screen here. These are the values that if you analyze your country rock, you can start to get excited about for your lithium, cesium, rubidium, and tin. Now I'm going to be talking about the Tanco-Pegmatite, which is intruded into an amphibolite. And this research was done by Morgan in London in 1987. And they found a few similar highly mobile elements have been pushed out into the country rock around Tanco. Fluorine, boron, lithium, rubidium, and cesium mainly. And they found that 3 main mesosomatic events occurred from the Tanco-Pegmatite. The first being a boron, fluorine, and lithium enriched event, which formed your ferruvite dravite schorl sequence, which is your tourmalinization around the pegmatite itself. Then there was this potassium, rubidium, cesium, and fluorine enriched event, plus or minus lithium, which formed your biotites in the country rock. And finally, we get a propylitic alteration sequence with your epithote, chlorite, titanite, calcite, and clay assemblage. Now, lithium is associated with each of these stages to different levels. And the principal lithium sink in the country rock is in the form of holmquistite or biotite. I've put a picture of holmquistite in the bottom right hand here. This is another great exploration indicator you can keep your eye out for. It's usually this purpley blue needly mineral that can be found at the contact of lithium-bearing pegmatites, dependent on the mineralogy of the country rock. And from this study, they found that at least 9 meters away from the pegmatite contact, they found this holmquistite. However, from unpublished thin section petrography that me and a colleague did, we found that holmquistite can be found actually a lot further away than this, and the halo might be much more extensive than was originally thought. So understanding your mineralogy and geochemistry is also highly important for your mining, because it helps you understand your assay values and your drill core a little bit better. So if you've understood your geochemical trends in your paragenetic sequence, this means that you can help identify anomalies in your assays and explain why. So if you take an assay value of your apolitic albite, for example, so your sodium enriched metasomatic units, sometimes these can be elevated in lithium, and that has been found in some instances to be linked to microspodumene crystallization in the unit. Obviously not in large quantities, but that can help explain your blip in assays. You can correlate your assays to your mineralogy as well. There are lots and lots of various lithium phases which can crystallize in pegmatites. So elevated assay values don't necessarily mean that it's spodumene showing up in your values. So it could be lithium micas, it could be phosphates, it could be a whole variety of things. So with this information, you can help target the exact phases you want. This can go a step further as well. If you have a great understanding of your system, you'll have really good core logging schemes that your geologists can implement. And having a really systematic logging scheme from the beginning is really important for later stage exploration and drill core plotting. And essentially, if you establish a really good logging scheme early, you can correlate the zonation trends and relationships to the type of lithium mineralization that you actually want to mine. And these two factors come together and help target where you want to mine at the end of the day. So understanding your geochemistry is also important for your metallurgy, because it helps you understand what zone your mineralization is in, what it's associated with, and this can help explain trends. So for example, if one side of your pegmatite has elevated sodium values, this could be due to secondary breakdown processes. Or if some of your spodumene has elevated iron values, this could be due to country rock contamination. So understanding these relationships help you better forecast what's going to happen in your metallurgical processing and how that's going to influence your the quality of your product at the end of the day. And when it comes to lithium metallurgy, it turns out size actually does matter. So with spodumene, the finer your crystal size, the harder it is to liberate during processing. And the texture and origins of this play a large role. So I've mentioned microsquee before. I'm going to talk about specifically why this is so bad for metallurgy in the next couple of slides. And understanding why and how your spodumene is texturally variable is important for economic processing, because you can better understand how much lithium you're going to liberate at the end of the day and forecast if you're going to have any issues. So here is the typical spodumene processing cycle. We start off underground at the Pegmatite, where you can blast out your material and truck it up to the surface. You then take your rock, put it through a jaw crusher to roughly pebble size, where it can then go through a heavy media separator. And this is essentially a tube that spins round and spits out the rock, and then the table shakes, and this can produce two main piles, your sinks and your floats. This material then goes through the ball mill, where it's ground down to the right size, and then goes through sizing classification. And ideally, we want between about 30 microns and 212 microns. Any smaller than this will produce slimes in the process, and any larger than this, your grains are really going to have a hard time floating to the top during the froth flotation process. So froth flotation then takes place where the lithium binds to the surfactant. It's then brought to the surface and then it's skimmed off, and then you have your wet lithium concentrate, which is then dried. So microsquee, as I previously mentioned, is incredibly hard, very intergrown with quartz, a very micro scale feature, and this leads to three main issues. The first, during mining. When I'm at Tanco, the underground miners always tell me that they know they've hit a face of microsquee because all of their machines start breaking underground. So due to this very hard nature, machines break, strainages occur during drilling and blasting, and this leads to additional expenses and part replacement. In the mill phase, microsquee is very, very hard, so it's more resistant and energy intensive, and it takes a lot of time to process, and it often has to be reground multiple times so you can actually liberate the lithium. And then finally, poor recovery arises as well, because if you think about this fine symplectite texture, you have your spodumene and quartz linked to one another. So in these fine particles, it's very common that there's a lack of surfactant, a lack of surface area to bind to the surfactant, so the bubbles can't actually take up the lithium to the surface. So thank you so much for listening. I've just put a picture on the screen of the Catriona consulting team, me and Lot Koopmans. He's more of the structural side of things, and also Tanya Martins, who's one of my fantastic supervisors who helped review this presentation today. So yeah, I would love to answer any questions that anyone has, and thank you for listening.
Thank you so much. That was awesome. And I'm such a fan of memes in presentations. So thank you for the great entertainment as well. I love that.